or one of each of these, and you had to sort of make your argument. Let's talk about why we're doing these argumentative things in geometry, because this sort of doesn't relate to anything we've done so far this year, right? So what were some of the things that you used in your arguments to sort of help you make your point, help you prove your point that you were trying to? So you use facts, such as with Beyonce, you said the number of Grammys or things like that, or I'm trying to think of other facts. It's just been around or been in the thing for longer, or you said PUBG was as a more, or was new, older than the original one, or older than the other one, whatever it was. Okay. What are some other things we use? We use facts.
It's kind of like opinions.
Opinions were thrown in there, okay. Anything else?
It's kind of what you prefer.
So prefer opinions, okay. Turn your emotions, your ethos, not pathos. You want to throw in those English words in there, get the logos, ethos, pathos, whatever, all the other ones are. All right. What?
How do you know we're learning about that?
Are you learning about that right now?
Yeah.
Oh, that's cool. I didn't know that. It's just coincidence. Okay. So we're going to talk about doing sort of arguments in geometry, but they're not necessarily arguments like where you have two objective points, like Fortnite or PUBG. It's objective. It's which one you really prefer, like Gage said. Compared to, we're going to start doing more subjective things. We're proving things are true. So basically with these, you're going to be given some information, and we're going to have to prove that something's true because of that. Say this angle is 90 degrees, you're going to have to prove that this is a square, or this shape is a square, or prove that this triangle is the same as that triangle. So these proofs, you're going to have to sort of look through the information that we know. We're going to use that. So when we form these proofs, we're going to use something called deductive reasoning. So we're going to use facts, definitions, properties, logic. We're going to put all of this together, and we're going to sort of funnel it into an argument. And so we're going to have to look through what information do we know, and how can we use that to make a conclusion about our point? How can we use the fact that this is a right angle to prove that this triangle has 180 degrees? How can we use the information that these two sides are the same to prove that these two triangles are actually the same thing? And so with this, it's going to be a lot of thinking. It's going to be a lot less math. It's going to be a lot less solving for x, or a lot less solving for this angle, but a lot more thinking and knowing. We're going to have to use a lot of definitions or a lot of properties. So knowing that these two angles are alternate interior, knowing that these are vertical, knowing that these two sides are congruent because of perpendicular bisector. We're going to have to use a lot of logic and a lot of definitions and a lot of knowledge and a lot of thinking rather than having to solve for things. Not necessarily running through the same steps, but sort of looking at a problem and justifying how can I solve this or how can I improve this. And so some of the things we need, number one, facts. Facts are key, facts are important, facts are the number one thing we need to do in order to solve things. We can't prove anything without facts. You can't just assume that this angle looks the same as that angle, so I'm going to assume they're true. We can't do anything like that. We have to know they're true, we have to say why that's true, we have to say where we got this information from. Everything has to be justified. You can't just assume that these two are going to be the same. We can't just assume those lines look parallel, so they're going to be parallel. We can't do anything like that. Everything has to be from a fact, it has to be from a definition, it has to be from a theorem or something. You have to have a reason behind everything. So we're going to take all these facts, but I can't just spill a bunch of facts at you and say something is true. You have to organize it. We have to put it in order. You can't just say, you can't put one fact, you can't use one fact that utilizes another fact. You can't put them out of order. They have to be built upon each other. Using one fact to make your next statement, and make your next statement, and make your next statement. So the order really matters with these. There's a funny picture of a chair that's put in a different order.
Is that an IKEA chair?
It probably was. No introduction. But the order you put something together matters. The order we put these proofs together matters. You can't just throw your facts out willy-nilly. We have to organize it and be able to build off your last fact you used to be able to make your next argument. Build off that last fact to make your next argument. It has a structure to it. just like order matters with order of operations, you can make an argument on which one of these are true. You can make a proof on which one is true based off your order of operations. So is 2 plus 2 times 3 equal 12, or 2 plus 2 times 3 equal 8?
What?
Why does it equal 8?
And
PEMDAS, order of operations, multiplication comes before addition. So 2 times 3 happens first, which is 6. So it's 2 plus 6, which is 8, compared to. But once again, order is important. You have to know the order of things. We have to know how we can form this logic in a cohesive, sensible order.
But they're the same problem.
But you have to do.
But we have order of operations that tells us which one comes first. Remember, please excuse my name at Sally or PEMDAS. Multiplication comes before addition, so if we have to do all the multiplication problems first. All right. So even though some things might seem really easy, you might be able to see something really quickly in math. And with these proofs, though, we need to list all of the steps. I can't just say LeBron James is better than Kobe Bryant. That's not an argument. I need to list the information, list the steps. How did I come to that conclusion? So with these proofs, we have to list how do we come to this conclusion? How does this proof make sense? How is this argument being formed? And so we need to list all of those steps. So once again, it's going to be a lot more writing things down on what's actually happening versus writing down the math or showing the math. So for those of you who just like to write the answer, it's not going to work. We have to show all of those steps. What did you do? How did you get there? Where was your thought process along this? And so it'll be a lot of writing. So let's just practice writing down these steps with just this first example. So we have to figure out what the angle of ABD is. So that's what we're looking for. What is that ABD angle? And some of us might be able to recognize what it is pretty quickly, but we have to figure out what that step, and we have to figure out what those steps are. How did you figure out that information? So whenever we do these proofs, step number 1 should always be to write down what your given information is. What do you know for sure? What are you absolutely positive is true? So angle DBC equals 60 degrees. We know that. It's right there. It's told to us. We can see that. That's plain as day. What else do we know for sure? So ABC is 90 degrees. We know that for sure. It's a right angle. We see it. We're told that. There we go. So these are two things that we know directly. We can just see them. They're there. We know it. What was that? We use the vertex. Okay.
30 degrees.
But why? But the listing
Because
step.
90 minus 60 is 30.
All right, but you skipped a step. These two added together equal ABC. So we have to remember, list every single step in the process. Angle ABC equals angle DBC plus angle ABD. We have to make sure we list all of those steps. So angle ABC
Plus that,
equals this one plus this one. All right, now that we have this piece, use previous information you've stated and cycle it through to help you solve. The previous information, ABC equals 90 degrees. We can substitute that in there. We know that's previous information. DBC is 60 degrees. We can throw that in there. And we're looking for ABD. Now, Colton, we can come to the part where we can subtract 60. Which leaves us with 30 equals angle of 80. Now we've proven what the measure of ABD is. But the main thing that we need to go through is every single step. You can't just write down ABD equals 2. I mean, we won't be this was obviously a simple, very easy thing to do. So we won't be doing things like this. We'll be doing things that will involve more steps and more reasoning. But we can't just jump straight to this conclusion. You have to list every step on where you got there. You can't just say this, you have to say why. We okay with this so far? So once again, it's going to be a lot of thinking. Okay, we're going to stretch your brain, we're going to make you think harder, you're going to become a superhero with the mind. So proofs are typically a challenge for a lot of students. It's different from math that we learned before. Typically, you're used to giving a problem, you know the steps, you know how to solve. This is different. You're given a situation, you're given a little bit of information. You have to utilize that information, think off of it, write down what your thinking is, and use that. It's still solving. You're still solving. You're still trying. You have a problem. You're still solving it. It's just a different way of showing your work and a different way of expressing it. Did I talk about counterfacts? I skipped this, didn't I?
Yes.
All right. Counterfacts. So counterfacts are important. We need to know what things are. Sometimes we're proving things aren't true. Sometimes we're proving that this isn't a square. Sometimes you're proving this isn't a pair. These lines aren't parallel. Using that, you can use counterfacts. If you can list an example of something not being true, that is enough proof to say that it is not true. For example, can we give an example of a rectangle that's not a square?
Just add it on everything else.
So that's a rectangle.
All sides are not equal.
That's a rectangle, but all the sides aren't equal, so it's obviously not a square, so that's a counterfact of rectangles are not always squares. And so sometimes we're trying to prove things are, sometimes you're using facts, sometimes you're using counterfacts to make your statement true. Sorry, I forgot about that. All right. So this is an example of a proof. You'll be given a piece of information. I'll say given some piece of information, and then I'll say what you're trying to prove. So we are given that angle 1 is congruent to angle 2. We're trying to prove that H is parallel to K. So this little symbol, it's like a little squiggly symbol with an equal sign below it. This means congruent. So once again, in geometry, our word congruent means the same. So anytime you see this, know that this is saying angle 1 is the same as angle 2. They're the same angle measure. That's congruent. That's an important symbol. We'll want to be able to recognize that. It looks like your equal symbol with just that little squiggle line. The two lines, that's parallel. So mathematicians, with these proofs, we need to write down all of our steps, but it doesn't mean we have to write down every word we're saying. Sometimes we like just shorthand things. So we throw in a lot of symbols there. So we'll throw this in instead of using the word congruent. We'll throw this in instead of using the word parallel. Just to make it quicker with writing down all of those steps. And so what this is saying is, our given information is angle 1 is congruent to angle 2, and then we're supposed to prove H is parallel to K. So we're trying to prove these two lines are parallel. That's our whole goal. That's the end goal. What we're starting is angle 1 is congruent to angle 2. So with these proofs, I had a professor sort of describe them as crossing a stream. So you're on one side of the stream, you have to get to that other side of the stream. We have to figure out what are the steps you need to take, what are those sort of stepping stones that you can step to get from one piece to the next, to be able to solve. Sometimes you might work one direction, sometimes you might work another direction. But we're going to sort of see what we can do in order to get us from one side of the stream to the other. How can we get from this side to my proof side? How can I find that conclusion? So once again with proofs, we always want to start with the facts that we know. What do we know for sure? What's told to us? So that's what we're trying to show. We're trying to show we're parallel. We don't know that at all yet. That's where we're trying to end up. We're given that angle 1 is congruent to angle 2. Okay. So if angle 1 is congruent to angle 2, what does that make those two angles? What was that, Alex? Okay. So because angle 1 is congruent to angle 2, these are alternate interior angles based off of their location. So based off their location, based off the fact that they're congruent, this means these two are alternate interior angles, just like what we thought about last week, our different type of angle pairs. We recognize one of those, they're alternate interior angles. When is the only time we can have alternate interior angles though? What has to be true to have alternate interior angles? Our lines have to be parallel. We can't have alternate interior angles without it. And so, the conclusion we can make is because we have alternate interior angles, H is parallel to K. So with these proofs, something you'll notice is every statement you make needs to have a reason. So our 1 being congruent to 2, the reason was just because it was given information. 1 and 2 being alternate interior angles was given to us because we were able to make that reason because these two are congruent. The lines are parallel was given to us because we know they're alternate interior angles. So we're always using that piece of information before. Specifically, all of the ones we're going to use proofs throughout geometry. We're going to do triangles, squares, circles, parallelograms. We're going to be proving a lot of things. And we're going to show all of that. We're going to start with parallel lines, though. That's what we're going to be proving. So with these parallel lines, whenever you're trying to prove two lines are parallel, all we need to do is show one of those angle pairs, alternate exterior, alternate interior, or consecutive, corresponding. If you can show one of those angle pairs, then you can prove those lines are parallel. Or not parallel, depending on whether it's not true or not. But that's the main thing. We're trying to show that. We're trying to figure out how can we show that information, how can we get to that information based off of what we know. And so this is one way to write down a proof. Sort of write down in a paragraph style, say like angle 1 is angle 2, or congruent to angle 2, because of angle 1 is angle 2. So you can like write down all these sentences. Another way that we use more common is called the 2-column proof. So your proof is going to be separated into 2 columns. One column is going to be your statements. The other one is going to be your reasons. So your statements is what you're saying. Like, I'm saying angle 1 is congruent to angle 2. The reason is the because. So angle 1 is congruent to angle 2 because so-and-so, because they're vertical angles. Angle 1 is congruent to angle 2 because they're something's occurring. J is parallel to K because these are alternate exterior angles. So it's always going to be your statement, and then what's your because? What's your reason behind that statement? And so to start off with these parallel lines, or to start off proving this, we need to think, what is our given statement? So what are we told in this problem?
3, angle 3.
So we're told angle 3 and angle 5 are supplementary. We're trying to prove J is parallel to K. So we're trying to prove these two lines are parallel. All we know is these two are supplementary. Yeah, that's equal to the mid.
So we can just do the same thing through 5 and 1 to the left because they're the same.
But we got to get there. And we have to say how we got there. So let's write down these steps. So once again, you might be able to see it. You might be able to know it. But because you can see, that means it's going to be easier to figure out what the steps are. We have to say why. All right, so your statements, first statement should always be your given information. So angle 3 and angle 5 are supplementary. We unfortunately do not have a symbol for supplementary, so I'm just going to write sub. So angle 3 and angle 5 are supplementary. The reasoning behind that was given information. We're told that from the start. We don't need to worry about that. All right, that's all we know to start with. We're trying to use that piece of information to help, and what else we see, to help us say J and K are parallel. What can we do? So what other information can we glean from this problem, or reason?
Because you can flip it.
Flip what around?
I mean,
1 to 3 and 4. What do we call that? Vertical. So vertical angles means that 3 and 4 are going to be congruent to each other. Three and 4 are congruent because they're vertical angles.
So they're the same.
All right, so 3 and 4 are the same. We know that because they're congruent.
So 5 and 6 would be the same.
5 and 6.
Yeah, 6 would be at the bottom.
Okay. Let's stick with the numbers we have, though, in this situation. Remember, we're trying to prove that J is congruent to K. And the way we can do that is showing any one of those angle pairs, those vertical or those parallel line angle pairs that we've had last week. Can we find it?
Same side and
So we can show same-sided tiers. We need to show these are supplementary. How can we show they're supplementary, though? We know 3 and 5 are supplementary. We know 3 is the same as 4. Can you make a conclusion based off of that? Is that enough to say that angle 4 and angle 5 are supplementary? And so our reasoning behind that would be because angle 3 is congruent to angle 4.
That's a car dealership.
Right. So now we know 4 and 5 are supplementary. How can we use that piece of information? Remember, we're building off of what we've talked about. We're building off of what we said before. How can we use 4 and 5 are supplementary to help us get to that next step?
Prove that.
But is this enough to prove that? How can we use that piece of information? We're really close to the other edge of the bank. We're really close to the other edge of the river. We just get that one other stepping stone in between us and that one. What? All right, so 4 and 5 are supplementary. What type of angle pair is this?
Consecutive.
Consecutive. So we can say 4 and 5 are consecutive. The reason being 4 and angle 5 are supplementary. So because we know they're supplementary, we can say they're consecutive. Once again, before you can make any conclusion, you have to have the reason. So because they're supplementary, we have them consecutive. Now because they're consecutive, can we make a final conclusion? So our final conclusion is J is parallel to K because angle 4 and angle 5 are consecutive. So with these problems, you're always building off of what you said in the past. We're always building off of our previous information. So if we see it, it's kind of like a zigzag. So we started with some given information. We were able to glean the vertical angles, and then we were able to use that to help us figure out the 4 and 5 are supplementary. And then we were able to use that to help us figure out that 4 and 5 are consecutive. We were able to use that to help us prove that J and K are parallel. So we're always sort of using that previous information. Once again, order matters. You can't just list out the facts. We have to list them out in the correct order and figure out what is the reasoning behind this next piece of information. On your state tests, what they tend to like to do is they'll give you part of it, and they'll give you a 2-column proof like this, but they'll leave this part blank and this part blank. And they'll have a bunch of little things off on the side that you can sort of fill in. You can sort of click and drag to fill them in.
They'll give you bits and pieces.
They'll give you bits and pieces, and they want you to fill in the rest. And they'll say, okay, why was this person able to make this conclusion? Based off this reason, what statement can be made on this spot? That's what they tend to like to do. Sometimes they might give you a completely blank one where you have to fill it out all by yourself. But most of the time, they'll give you bits and pieces that you have to fill in. And they'll have little tabs like vertical angles or 3 and 5 are congruent, things like that on the side that you can click and drag into the spaces. That tends to be how they do it on the state test. Yes. Yes, on the computer. But the main thing with these is really just being able to recognize what am I trying to show? Where's my end goal? And how can I get to that end goal? Sometimes you might see, okay, if I can just show this, I can make my proof. Now how do I get to that part? And so sometimes it's working at both sides. So you're on your one side of the river, you need to get on the other side of the river, you need to find those stepping stones. So you might be this far in, and then you realize, wait, if I can just show this piece of information, I know I'll be able to get to there. But where's your gap to get there? So sometimes you're going to work from both angles. Sometimes, oh, if I can show this much, well, where's that next step? And so with these proofs, it's a lot of thinking, it's a lot of logic, it's a lot of reasoning, it's a lot of figuring out how can I show this is true. And it takes a lot of practice. It's one thing just to be able to see the problem. It's another thing to be able to reason through why it works. And parallel lines are typically the easier thing to start with, and so that's why we're starting our proofs here. We're going to use them to show triangles are the same. We're going to use them to show a square is not a square, or is a square, or it's in a rectangle, or this quadrilateral is a parallelogram. We're going to make a lot of proofs. But this is just sort of going to be our basic building block. But always, we're going to have to rely on information we learned in the past. We're going to have to rely on those parallel angle lines, or angle pairs that we learned about. Most of the time, unless it's like a completely new unit, then, for example, right after triangles, we'll go into like squares or something like that. But you'll still use triangles and squares.
I think we're going to learn a lot more about triangles and squares, but I'm thinking
We will learn a lot. We will learn a lot about triangles.